Welcome to Oceanic and Polar Experts. In this episode, we are thrilled to feature an interview with the highly distinguished professor and researcher, Roger Grimshaw. Professor Roger Grimshaw served as a professor of mathematical sciences at Loughborough University in the UK and was the director of the university's Centre for Nonlinear Mathematics and Applications. He has also held honorary positions at the University of New South Wales and University College London. Professor Grimshaw's research focuses on the theory of linear and nonlinear waves in the atmosphere and oceans. His expertise has made him a regular invited speaker at international conferences, and he has served on the editorial boards of numerous prestigious journals, including the Journal of Fluid Mechanics, Theoretical and Computational Fluid Dynamics, Nonlinear Processes in Geophysics, and Wave Motion. Additionally, he has served as chairman of the Division of Applied Mathematics of the Australian Mathematics Society and on national and academy advisory committees for mathematics and meteorology. In recognition of his significant contributions to Australian society and science in applied mathematics, Professor Grimshaw has been awarded the Centenary Medal and the ANZIAM, Australian and New Zealand Industrial and Applied Mathematics Medal. Unfortunately, due to several reasons, Professor Grimshaw could not join us for a direct conversation. However, he has kindly provided written responses to our questions, which I will share with you in just a few seconds. Stay tuned for some fascinating insights from one of the leading minds in the field. To begin with, can you tell us a little bit about yourself and what you do? I am employed a mathematician. For many years, I worked in a university in Australia from 1965 to 1999, and then in England from 2000 to 2020. I have taught at all levels, but my main interest was research, publishing papers, supervising research students, taking part in conferences, editorial work, and other professional activities. I have mainly worked on the theory of waves in geophysical fluids, water waves, internal waves, and so on to the planetary scale, continental shale waves, and ocean eddies. Second question: why is it important to study waves using mathematics? Historically, waves and mathematics are inextricably linked. From Newton, gravity and tides, to Gauss, Euler, Poincare, Stokes, Boussinesq, Rayleigh, Kelvin, through to the present day. The second half of the 19th century saw some amazing theoretical developments. The discovery of solitons, and the integrability of basic wave equations, such as the KdV equation and the nonlinear Schrödinger equation, each linked to real physical phenomena, such as internal solitary waves and rogue waves. At the same time, chaos theory emerged. All these stimulated by the advent of high-speed computing. What do you think of the connection between the physical world and mathematics, and the relationship between math and physics? The connection between the physical world and mathematics is very deep and historically long-standing. There have been periods, such as the mid-19th century, when some mathematics became very abstract. But the discovery of solitons and the advent of chaos theory have changed that. And today, mathematics is firmly rooted in real-world phenomena. The difference between mathematics and physics has always been quite blurred. At the undergraduate university level, general physics departments do experiments and mathematics departments do not. But even that difference begins to disappear at the postgraduate and research level. At Cambridge, the Department of Applied Mathematics and Theoretical Physics where I did my PhD, is renowned for its fluid dynamics experiments. I even took part in a major fluid dynamics experiment myself at the Coriolis platform in Grenoble, where we investigated the effect of rotation on an internal solitary wave. The experiment verified the theory we had developed, and I should add that although we arranged the experiment, it was in fact done extremely well by the laboratory technicians in Grenoble. In so many years of digging into this field, what are some interesting findings from your research? That is really for others to say. I have always worked on waves, linear and especially nonlinear, with a focus on geophysical applications. These include oceanic water waves and internal waves, which, like water waves, exist due to gravity, but the displacement is in the interior of the ocean and not at the surface. I have also worked on atmospheric internal waves and larger-scale oceanic waves such as continental shell waves and planetary-scale water seas, oceanic eddies. Much of my research, especially on internal solitary waves, was to examine how waves adapt to their local environment. For example, how do internal solitary waves respond to a variable ocean depth? For me, one highlight is the development of the variable coefficient KdV equation to describe the propagation of internal solitary waves in the real ocean, and the asymptotic analysis of that equation. For my internal solitary waves research, other highlights are the elucidation of the effect of rotation on internal solitary waves using the extension of KdV to the Ostrovsky equation and the Coriolis experiment. The establishment of the forced KdV equation and its undulable solutions as a model for the generation of internal solitary waves by the interaction of tidal flow with a sharp topographic feature, and using asymptotic theory beyond exponential order to explain renouncers between internal wave modes and similar problems. Now that I have retired, I work with a colleague in Thailand on wind waves, looking at the development of wave pockets using the nonlinear Schrödinger equation forced by an instability due to a prescribed wind. During your research, what are some challenges you faced and how did you overcome them? I will not describe this exactly as challenges, more as landmarks. I did a conventional science degree, Bachelor of Science and Master of Science, in mathematics at Auckland University in New Zealand, and then went to the Department of Applied Mathematics and Theoretical Physics in Cambridge to do a PhD. That was a huge change, moving from a familiar, comfortable environment to a high-pressure research facility. Then, as now, the Department of Applied Mathematics and Theoretical Physics was a world leader in applied mathematics and especially in fluid mechanics. When I arrived, I had not done any real fluid mechanics and was allocated a supervisor, Dr. Freelander, an expert in sound waves, then extended his research into general relativity. I followed him into sound waves, looking at the interaction between waves and obstacles. I learned much from him and was fortunate that he was a kind, generous, laid-back person. With his help, I did a postdoctoral year at the Courant Institute in New York, world famous for both pure and applied mathematics, before I left for my first academic year at the University of Melbourne in Australia. The challenge then was to maintain and develop a research profile. At that time, there was no internet and no email, but I kept in touch with the exciting developments in applied mathematics, solitons, integrability, chaos theory, and so on. Through reading journal articles in the well-stocked library and frequent 6-month sabbaticals in England, mainly the Department of Applied Mathematics and Theoretical Physics and UGO. This was the period when I began working on nonlinear internal waves, as in contrast, water waves were being heavily studied. As well as sabbaticals, I was able to go to major international meetings. An especially notable one was a IETUM, International Union of Theoretical and Applied Mechanics meeting, in Tallinn, Estonia, where I made direct contact with Ostrovsky, Palanovsky, and Stepanians from Nizhny Novgorod, Russia, whose works on nonlinear waves were similar to mine. They became close colleagues in Australia and later in England. Another landmark was my move from Australia to Loughborough University, England, in 2000 to take up a professionalship there. That was not an easy decision, but one that worked out personally and professionally. At that time, UK was still in the EU, and a major attraction for me was the possibility to develop EU research connections and to enjoy European culture. Do you have any recommendations of resources that could potentially help us understand this topic further? As always, Wikipedia is a good place to start. Online searches for internal solitons would show relevant articles on internal waves in the marine popular literature and in journals of the oceanographic community. I'm sure you are aware of this. For the underlying mathematics, a search for rogue waves would show articles on the nonlinear Schrödinger equation, and similarly, a research for solitons would show articles on the KdV equation. These are often written by scientific experts seeking to spread the word to a wider community. You have published so many papers after you retired and are still doing research today. How did you manage to be that productive? I have published 357 referred journal articles, 7 books, 31 chapters in books, and 38 conference proceedings. I can't say how many since I retired, as I'm not sure when I formally retired. This publication record is large because over the 60 years of my academic career, I have had many collaborations and co-authors, PhD students, postdoctoral fellows, and colleagues local and international. But now that I have really retired, the only topic I keep working on is wind waves with a colleague from Thailand, a project I started in 2017. It is a fascinating topic with a long and controversial history, and with many unanswered questions even today. What is a common myth about your job or industry? It is commonly thought that mathematicians are nerds, interested in only abstract concepts and with no interest in the real world. That is demonstrably generally false, historically and through to the present day. Where there may be some truth in that for some pure mathematicians, applied mathematicians and most pure mathematicians are motivated by real-world problems, quantum mechanics, general relativity, astrophysics, mathematical biology, theoretical chemistry, through to the classical subjects of fluid and solid mechanics can be found in mathematics departments and research centers. I firmly hold the view that there is no boundary between pure and applied mathematics, a view espoused by the founders of the famous Current Institute and held in most UK universities. Do you have advice for those interested in your field? What are some important skills needed for this field? Being bold and willing to tackle problems from all angles, theoretically, numerically, and experimentally. For applied mathematics, a solid grounding in calculus-based subjects, and also, in these days, in computation. Although I myself never had that and have relied on colleagues for numerical simulations, for oceanography, a solid grounding in classical fluid mechanics is needed, although again, I myself didn't get that at the undergraduate level. Is there anything else that you would like to share with us? No, I think that I have said enough. Thank you for the opportunity.